I'll get started. I will begin. So, Heavenly Father, we thank you for this day, and I thank you for this class and this time we have to meet together and study your creation. Help us to glorify you what we do and understand a little more about linear transformations and their matrices, Lord. In your name I pray, Lord Jesus. Amen. So we have talked a little bit about what is a linear transformation. Big thing, of course, is that any linear transformation of column vectors we can write as a matrix multiplication, right? The formula can be written in that way. And so far we've only looked at the matrix with respect to the standard matrix, right? So like basically example 1, if I had, T of, well, let's see here if we can figure something out. Suppose you have T of, let me make a kind of weird example here for us for a second. Suppose we have T of minus 1, 0, 1 is equal to, minus 1, 0, 1. Suppose we have T of minus 2, 1, 0 equal to, let's say, 4 times that. All right. In other words, that'd be what? That's minus 8, 4, 0. All right. And continuing with this weird example, T of 3, 0, 2, let us suppose that that is equal to 6 times 3, 0, 2. All right. So that would be specifically 18, 0, 12. All right. So my question then is, if this is the situation, what's the standard matrix? Find the standard matrix of T. So this is kind of a tough question because I've given you such kind of roundabout information, right, about this linear transformation. How would we solve this? Any ideas? See, so in a problem like this where I don't know something, it's oftentimes useful to give something I don't know a name, right? So let's call the standard matrix of T, let's call it A. Right? Usually the standard notation for it is T with brackets, right? All right. Anyway, so we have A, and let me call this vector. Let me call this vector V1. Let me call this vector V2. Let me call this vector V3. So what we have is A V1 is equal to V1. We have A V2 is 4V2, right? And we have A V3 is 6V3. That was what I gave you, right? So in this, we can combine these three equations into one matrix equation, right? This can be written instead as A times V1, V2, V3 equals to what? V1, 4V2, 6V3, right? And so we could solve for A, right? What would A be equal to? We should just multiply by what? The inverse of that matrix, right? On both sides, we could solve in that way. So multiply this by the inverse of this matrix, whatever that is. Now that's a little bit unpleasant, but we could do it, right? Let's work it out. So this matrix V1 was minus 1, 0, 1, 4. I'm sorry. So I'm writing out the blue matrix here. So minus 1, 0, 1. 4V2 was minus 8, 4, 0. 6V3 we said was 18, 0, 12. Right? What's the inverse What's the inverse of V1, V2, V3 inverse, right? How would we calculate that? Do you guys remember? We would want to calculate the reduced row echelon form of the matrix 1, 2, 3, minus 1, 0, 1, 2, 1, 7, concatenated with the identity matrix, right? And after about 6 row operations, you'd get to the following. Oops. After about 8 row operations, you'd get to the following. 1, 0, 0, 0, 1, 0, 0, 0, 1. And we've got a 1/8, minus 11/8, minus 1/4, 5/8, 1/8, minus 1/4, minus 1/8, 3/8, and 1/4. Did I do something wrong, or what's going on here? Oh, you're like, wait a minute, what's that matrix? Oh, 1 second. Did I pick up the wrong paper? I picked up the wrong paper. Sorry. True. We can save this for later. Let's just keep this for later. I don't want to write that again. We're just going to save that for later. This is true, but irrelevant. Sorry, wrong paper. Try that again. Roof of this time, the one that's relevant, 1, 0, 1, minus 2, 1, 0, minus 3, 0, 2, right? That's better. That's actually this, then that, put it as a matrix, yeah. Wait a minute. Oh, there's no minus on the 3. Okay. All right, so that row reduces to the identity. And this matrix over here, which happens to be after 6 row operations for real this time, minus 2/5, minus 4/5, 3/5 for the top row, 0, 1, 0 for the middle row, and then 1/5, 2/5, 1/5. So there you go. All right. So that is the, that's the inverse we're looking for here, right? So I can put that down. I get what? I got minus 2/5, minus 4/5, 3/5, 0, 1, 0, 1/5, 2/5, 1/5. All right, so I'm going to do, let me show you guys something. If you have a problem like this, one thing you can do to not be working with 9 equations with fractions, if you've got a common fifth everywhere, what's something we could do to simplify the arithmetic a lot? I'm giving you guys a pro tip. A life hack. So, is it too early for life hacks? 1/5, pull it out here like that. That makes this a minus 2, a minus 4, a 3, a 1, a 2, a 1, and be careful, what's the 1 have to become? A 5. All right. Now we can multiply these matrices, right? Let's do it. What do we get? I get what? 2 plus 18, also known as 20. I get 0. I get minus 2 plus 12, also known as 10, for my first column. I get 4 minus 40 plus 36. I think that's 0. Next one I get 20. Next one I get minus 4 plus 24. I think that's also 20. I get minus 3 plus 8 to 15, I think. You guys tell me if I'm wrong anywhere, okay? 0. And 3 plus 12, 15, right? Well, that's cool. So apparently the matrix we're looking for is 4, 0, 3, 0, 4, 0, 2, 4, 3. There you go. That is the matrix, right? Which has these facts about it, right? And has that standard matrix. Thought it'd be good for us to do an example which is a little bit tricky, right? I think it's a little bit tricky. We'll come back to this. So, given linear transformation, say t from Rn to Rm, and also S from Rn to Rm, we can define t plus s. We can define t minus s, right? We can define a constant times t. How do you define these new transformations from old? So I'm going to spend about 10 minutes talking about new transformations from old here. There's not too much to say. We need to talk about how to add, subtract, scalar multiply, and then compose linear transformations, all right? So let's do that. Then we'll come back to my example 1 in a little bit. So this is not complicated, guys. What do you think the definition of t plus s of x is? It's what? Oops. So we define addition pointwise. We define subtraction pointwise, right? We define scalar multiplication pointwise. These are all definitions, right? And so check this out. The standard matrix of t plus s, what's it going to be? How do you think we'd find the standard matrix of t plus s from the standard matrix of t and the standard matrix of s? It's just going to be actually the standard matrix of t plus the standard matrix of s. And likewise, if we had a minus here, like that. And if we want to find the standard matrix of the scalar multiplication of t, we just simply multiply the standard matrix of t by that scalar multiple. The proof of these assertions is like pretty simple. Let me show you it. I'll do all three at once if you guys don't mind. So what is column, let's say column J of the standard matrix of, let's say, CT plus or minus S? What would that be? How do we calculate the standard matrix? Do you guys remember? How do we find the column? We simply do what? We operate on EJ, right? So this would be CT plus or minus S on EJ by definition of standard matrix. That's how we find the jth column. And then by definition that I just gave right here, that's C times TEJ plus or minus S times EJ, which, by the way, is C times column J of the standard matrix of T plus or minus column J of the standard matrix of S. But if the jth column of these two matrices are equal for arbitrary J, that means the two matrices are equal, right? So this tells me that the matrix CT plus or minus S, the standard matrix of that, is equal to C times the standard matrix of T plus or minus the standard matrix of S. And if you look at the special case of C equals to 1 or S equals to 0, we get the claims I just made, all right? So Nothing especially shocking here. Composition is more interesting, though. Let's talk about composition of linear maps. How's that go? Here, I think we could benefit from an example. So suppose we have t of x comma y equals to x plus y, let's say 2x minus y and 3x. All right? So this makes t, in the current setting, going from R2 to R3. All right? Then we can let s, let's say, of u comma v be equal to, let's say, 2u and v plus u plus 7v. All right? So here I have s is a mapping from R2 to R2. All right? I'll let you guys catch up with me. So I'm going to study, for the sake of illustration, two linear maps, right? Are these linear? What do you guys think? Notice like t of xy is equal to what? 1, 2, 3, 1 minus 1, 0 times xy, right? And s of uv, we got ourselves a 2, 0, 1, 7 uv, right? So this is what? This is the standard matrix of t. And over here, you got the standard matrix of s. All right? So you guys tell me, what do you think? Is t composed with s? Or is s composed with t? Which one of these could I meaningfully calculate? The meaning is the same as pre-calculus. We talked about composition of functions, right? Remember? So this one, it means the output of s has to go into the input of t. I think that makes sense. See, because we have a two-dimensional output, two-dimensional input. S composed with t, on the other hand, is straight nonsense because t takes in R2, outputs R3. You can't feed R3 into s. So this right here is not even a thing. All right, that's not even defined. Okay, but t composed with s, we can calculate that. Let's do it. T composed with s. Here's the definition. It is simply defined to be t of s of uv. All right. So that's t of, well, s of uv was 2u, and then u plus 7v. In other words, that's equal to what? Identify x is equal to 2u, y is equal to u plus 7v. Substitute that into my formula up there. We get what? We get 2u plus u plus 7v, and then 2x minus y would be 2 times 2u minus y, which is minus parentheses u plus 7v. All right? And then 3x, well, 3x is 3 times 2u, right? So I'm just straight away I'm just calculating the composition of s and of t and s just directly. Let's simplify these formulas for our future reference, right? So what do we got here? I'm going to write it as a column vector for a change here. So I've got what? I got 3u plus 7v, and did I ever move the camera? I did. I have 4 minus 1, that's 3u, right? Minus 7v, and over there 6u, right? So what's the standard matrix of the composite here? Can you guys fill in the matrix for me? What is it? 3, 7, 3 minus 7, and then what? 6, 0. Did everybody agree? All right. Very good. So this would be the standard matrix of T composed with S, right? Observe, if we take the standard matrix of T times the standard matrix of S, what do we get? Standard matrix of T was 1, 2, 3, 1, minus 1, 0, and S was 2, 0, 1, 7. And if I calculate this matrix product, what do I get? I get 7. 3? Yeah, 3, 6, 7, minus 7, and 0. Oh, wait, they don't match. Why don't they match? Tell me why they don't match. Yeah, 2. What's 2? Here, we take the dot product of this with that. What do we get? We do not get 7. We get what? 3. Right? And then all is well in the world, right? Because this is in fact equal to what we just calculated over there directly. See that? This example is actually a theorem, all right? This is not an accident. There is a general theorem that we could prove here. Theorem. If we have T is a mapping from, say, Rn to Rm, and S is a mapping from, what is it here? Rn, well, it could be Rp to Rn, I guess. Then T composed with S. Let me just make sure, double check on my notation here. So S goes from Rp, this is S goes first, Rn, then T goes second, Rm. Sometimes I draw a picture like this just to check myself because sometimes I get lost with which one comes first, and I just have to double check that I'm forming a meaningful composition, all right? I think this one makes sense, though. The output of the inside function matches the input of the outside function, right? I want to say more, though. These aren't just functions, right? I'm assuming these are linear maps, linear transformations. If we have T and S like this, and they're both linear, this is just a parenthetical comment, okay? If this and that are linear transformations, then T composed with S is a mapping from Rp to Rm is linear transformation. And the standard matrix of T composed with S is equal to the standard matrix of T times the standard matrix of S. How would we, yeah? What? Oh, I thought I heard something. That was just a voice in my head. That's okay. My bad. So how would we prove it's a linear transformation? This is the easy part. Actually, everything's here easy. Everything's here the easy part. So how about this? We do T composed with S. To check that it's linear, we should look at Cx plus y, right? But what is that? By definition, this is T of S of Cx plus y, right? That's the definition of composition. We're assuming that S is a linear transformation, right? So we can pull out the constant and break up the addition there. So we have t of cs of x plus s of y, right? By linearity of s. So definition of composite linearity of s. But we also have linearity of t, right? So we can pull out the c, and then we have t of s of x plus t of s of y. Which is what? This is c times t composed with s of x plus t composed with s of y. Definition, composition. But this holds for all x and y and all constants, right? Therefore, what? Thus, the composite of two linear transformations is linear. So that's the first half of the theorem. How do you calculate the standard matrix of a linear transformation? What's our definition? The easiest definition, I think, is the one that's based on columns. So let's work it out. Like, what's the jth column of the composite? What do? We take the composite, t composed with s, and we feed it what? This is something you need to know, all right? I will test on this. How do we calculate the jth column of the standard matrix? Yep. Just EJ, right, yeah. And then what? This is what? This is T of S of EJ, right? So remember the theorem we had from the other day that's just always there? I mean, if you have a linear transformation and you're acting on a vector v, you can write that as the standard matrix of L times v. Still true here. This is equal to the standard matrix of T acting on the vector S of EJ, right? So think of the, and then applying that same principle a second time, this is the standard matrix of T times the standard matrix of S acting on EJ, right? But what is any matrix times the jth standard basis element? This is like basic matrix multiplication identity. This is the jth column of the matrix, the standard matrix of T times the standard matrix of S. So we have that the jth column of the standard matrix of the composition is the jth column of the product of the standard matrices. But J is arbitrary, therefore, you know, the standard matrix of the composite is the product of the standard matrices of the transformations composed. There you go. All right. In fact, this is not an accident. You could argue, and many do, that this is why we define matrix multiplication as we do, for this very reason, right? So you guys know what the standard matrix is now, right? It is, we feed the standard basis into the linear transformation, and that allows us to construct the so-called standard matrix. How about a non-standard matrix for a transformation? Can we define that? And what would we mean by that? Let's talk about it. All right? So we're going to talk about, excuse me, Rn. And suppose we have a basis for Rn, let's call it beta. All right, we talked about this the other day. We talked about how to calculate coordinate vectors with respect to a basis beta, right? Let me briefly review that for you guys. So definition, if beta equals to V1, V2, Vn basis for Rn, right? And this is the basis matrix, right? Is the basis matrix. Then, as we worked out the other day, the coordinate vector of x with respect to the beta basis, we could calculate by the inverse basis matrix times x, right? And what happens there is that we'd have x is equal to, like x1. Well, let me not use that. I use a different letter here. C1 V1 plus plus Cn Vn, where specifically the coordinate vector of x would be C1, C2, Cn. All right, and I introduced the barred basis and the barred notation as well in that previous lecture, right? So this is just a reminder. That's what we mean by that. So I need to give you a definition for the non-standard matrix. So if T is a linear transformation from Rn to Rn, then the matrix of T with respect to the beta basis, all right, what it's going to be is simply T of V1, the beta coordinates of that, T of V2, the beta coordinates of that, rats, and so forth and so on until we get to T of Vn, the beta coordinates of that. So this is the definition of the non-standard matrix of a linear transformation. And I'm just giving you the definition in the special context that we're talking about a linear transformation from n-dimensional column vectors to n-dimensional column vectors, all right? And I'm assuming that we use the same basis for the domain and the range, all right? We could talk about using a different basis for the domain and the range, and we of course could extend this definition to the context where we don't have the same dimension input and output, but I'll leave that for another day, okay? So this is it. And basically here's the deal. The theorem is this. If you want to calculate, let T act on X, all right, calculate the beta coordinate of that, well, that it turns out is equal to the non-standard basis times the coordinate vector of X, like this. What this means also, well, yeah. Let's see here. All right, so let's see if we can find a formula. So this is a theorem, which I could work out, but I think I'll resist the temptation to do that today. Can we find a formula for the non-standard basis besides its definition? Like if this is true, by the way, this is an alternate definition for the non-standard basis as well. You could take this as the definition if you'd like. Well, hey, why? I'll let you guys choose your own adventure. Which one do you want to be the definition today? A student's choice. Is this the definition or is this the definition? We can go either way. What do you guys want? The second one? Second one? Okay, second one is then. Definition. Theorem. Now I've got to prove the theorem. Oh, man. We'll get back to that. But before we get back to that, let's derive a convenient formula for finding the matrix here. Right? Think about this. We have everything we need. We'd like to relate my goal at the moment. Probably should tell you that. Relate the non-standard matrix to the standard matrix for T, right? It's not hard. So this right here is the basis inverse matrix times T of x. Right? Because the beta coordinate of a vector is the inverse basis matrix times the vector. On the other hand, this is equal to the matrix we're trying to find times, well, the basis inverse matrix times the vector x. Right? But, oh, well, we could do better over here too, right? What is this? We're trying to relate the non-standard matrix to the standard matrix, so I probably should bring the standard matrix into it. This we could rewrite as what? Standard matrix of T times x by the fundamental theorem of linear algebra. So what do we got? We've got this non-standard matrix. This is equal to, now we just got to have a little bit of creativity. Do you guys have any ideas for me? What should I do? Let me emphasize here, this holds for all x, right? Just to be clear, your definition was that this is for all x in Rn. It's not just there's a particular x, it's like every x has to make that go. Any ideas? If it holds for all x, what should I do? Just, I mean, essentially there's a theorem that if this holds for all x, it means that these two matrices have to be equal. Think about this. If I just let x be the, EJ, then I immediately get the column J of this matrix is equal to column J of that matrix. And if they have the same columns, they must be the same matrix, right? So we immediately get the inverse beta times standard matrix of T is equal to the non-standard matrix times beta inverse. And now I want to find a formula, right? So what is it? I solve for T beta beta. What you got?
Beta inverse times T times beta.
There we go. That's it. That is a formula that allows us to calculate the non-standard matrix from the standard matrix if we know the basis matrix and its inverse. My claim is that this is another way to calculate it, right? So I'll show you that now. This is equal to the basis inverse matrix times T beta, right? But that is, well, remember that this is also T of V1, V2, Vn, right? Which is what? T, standard matrix of T V1, standard matrix of T V2, standard matrix of T Vn. But that is what? T of V1, T of V2, T of Vn by definition of standard matrix. Well, I mean, there's a theorem, again, going back to the standard matrix times the vector is the linear transformation of that vector. And then this, by the usual matrix multiplication column by column rule, is beta inverse times T of V1, beta inverse times T of Vn. But my friends, that is nothing more than the coordinate vector of T of V1 all the way out to the coordinate vector of T of Vn. Which shows you that, in fact, my original definition is a derived consequence of our definition. So we have these two different ways of looking at the non-standard matrix. Now you might wonder, why would you do this? Why would you even care? Like, what's the point of looking at a matrix other than the standard matrix? Why would we care about this? Any ideas? Any ideas? What if the linear transformation you're looking at is really simple and you've just chosen the wrong coordinate system and you can't see the linear transformation being as simple as it actually is? Right? Maybe if we change coordinates, we can reveal the true nature of the linear transformation. We can reveal the hidden structure, right? So here's an example. If I can find it. Suppose we have T of x, y, z equal to 4x plus 3z, 4y, 2x plus 4y plus 3z. All right? This has standard matrix 4, 0, 3, 0, 4, 0, 2, 4, 3, like this, right? So there's my standard matrix. It's not too ugly, but it's also not terribly pretty. If I asked you, for example, is this matrix invertible? What's its range? Is it onto on? Is it onto on? Is it one? Is it 1 to 1? Is it onto? Like, what do you think? Or if I said, describe this transformation geometrically, what's it doing to R3? I think that's a pretty challenging question in its current format. All right? However, if we introduce the basis -1, 0, 1, -2, 1, 0, 3, 0, 2, then the basis matrix is -1, 0, 1, -2, 1, 0, 3, 0, 2, and we already calculated the inverse was what? It's over here. It's the -2/5, 4/5 business, right? Grab my paper. Right, we know the inverse, yeah? One fifth, 2/5, red fifths, blue. No, wait. Sorry. So there's your basis inverse basis matrix, and I'm telling you what happens is if we calculate this matrix product beta inverse times the standard matrix of T times beta again, what you're going to get actually is 1, 4, 6. on the diagonal and zeros otherwise. Because, by the way, let's go back and look at how I started example 1. See if you can understand what I did. So this was my V1. This was my V2. This was my V3. I had set up T of V1 is V1. I had set up T of V2 is 4V2. I had set up T of V3 is 6V3, right? If this is true, what's the beta coordinate of T of V1? What's the coordinate vector of V1? With respect to the beta basis. Here, let me give you a different one. If I had 17 V1 minus 19 V2 plus 3 V3, what's the coordinate vector of this? Do you guys know? This is something you ought to be able to do with minimal mental effort. Maybe you're not there yet, but like all we do, by definition, is we read off the coefficients. 17 minus 19, 3. That's what this means. Coordinate vector with respect to the beta basis. We read off the weights, that's the coordinate vector. So here I read off the weights. It's kind of boring. It's 1, 0, 0, all right? This one here, the coordinate vector with respect to beta T of V2 is what? It's 0, 4, 0, right? The coordinate vector of V3 with respect to beta, by the same token, 0, 0, 6. See that? That's exactly what we have there. Let me put it in different terms. If I have T of x bar 1, V1, plus x bar 2, V2, plus x bar 3, V3, just to give those labels, then this is equal to x bar 1 times V1 plus 4 times x bar 2, V2, plus 6 times x bar 3, V3. If I introduce x bar 1, x bar 2, x bar 3 as the beta coordinates for the sake of discussion, right? What's this transformation doing geometrically? You know, I don't know. I have no idea here geometrically, guys. Like what those axes look like. Like this is x, this is y, this is z, right? I could try to graph these. I mean, I'm going to regret this, but where does minus 1, 0, 1 go in my picture? Negative x, positive y, 0, z, right? So this is like the x bar axis, x bar 1 axis. I guess I could have just done x bar, y bar, z bar. It's too late. I've written what I've written. Yeah? Where does V2 go? Minus 2, 1, 0. Oh, my bad. This was supposed to go. Well, I guess it's kind of right. It was going up. So that's still, I guess, graphically illustrative of the problem here. So maybe this is a bad picture of x bar 2. X bar 2 axis, that's the way V2 goes. And V3 is 3 up. So it's kind of like, I don't know. I'll draw it in green. I'm going to draw it like it's over here, but I'm doing the best I can, guys, for these pictures. My point is, this transformation, it leaves vectors in the x bar 1 direction unfazed, right? It just maintains those. And vectors that are in the V2 direction, it rescales them by 4, right? Vectors that are in the V3 direction, it rescales by 6, and it does some kind of linear combination of those three things anywhere else. This thing that just happened here, so question, what's the determinant? What's the determinant of T? Can you tell me what's the determinant of T? oh, I'm sorry, we're out of time, but look, the determinant of the product is product of the determinants. The determinant of the matrix and its inverse is 1. So the determinant of T must be equal to the determinant of this matrix over here, which is what? What do you say, 24? 24, right. The trace of these matrices must also be equal. Anyway, what we did was we diagonalized the matrix. More on this later. Thanks, guys.